present my okay. Yeah, I'm going to go ahead and quickly share my screen. Okay. Yeah. So good afternoon, everyone. I'm Upasana, and today I'm presenting my work with my advisor, Aaron Cosette, and we are at the University of Colorado Boulder, and with Bailey Fosdick, who is in the Colorado State University. And I'm going to talk about sampling random graphs with specified degree sequences. So as you all might already know, random graph models are mathematical models that are widely studied in network analysis for generating uniform random graphs, where some constraint about the graphs to be generated, or specifically about the structure of the graphs to be generated, is specified from beforehand. For example, in case of order-Shreni random model, the number of nodes in the network to be generated and the network density is specified from beforehand, while in configuration model, the degree sequence is specified. There are other random graph models too, for example, the Chung-Lu model, where the degree distribution is specified. But in today's talk, we're going to specifically look at the configuration model, which is a mathematical model for generating uniform random graphs with a fixed degree sequence. So the degree of each node of the networks to be generated is known from beforehand, which is we know the number of stubs attached to each node. And the goal is to generate a graph uniformly at random out of it. Now, one of the cases where random graphs are used very often is as a reference distribution. So say, for example, we have an empirical network at hand, and we observe some network statistics. Say, for example, we compute its clustering coefficient, and then we want to ask the question that if we keep just the degree sequence the same and we randomize everything else, so we randomize the edges in the network, but just keep the degrees of the node the same, then do we observe the same or similar clustering coefficient? If we do observe same clustering coefficient, then in that case, we can say that the degree sequence alone is enough to explain the observed network statistic. On the other hand, if the observed network statistic is very different from the network statistic in the graphs with the reference graphs in the reference distribution that have the same degree sequence as the observed network, then we say that the high statistic or the low statistic cannot be explained by the degrees alone. And there must be something more interesting than just the degrees that's causing the observed network statistic. Now, one of the key features of the configuration model is that the graphs need to be sampled uniformly at random, meaning that of all the graphs possible with a fixed degree sequence, each graph need to have equal probability of being generated by the model. If some graphs have more probability of being generated than the other with a fixed degree sequence, then that is not the right way of doing it. That's a biased sampling method, and that is not what the configuration model is expected to do. And this is very difficult to come up with a generating method that can sample the graphs uniformly at random, which is why this has been an open question since long. And so one of the methods that people usually use for generating random graphs from the configuration model is this random stub matching algorithm, where random matching is made between the set of stubs of the network. So for each node, we know the number of stubs connected, right, to them. And what we basically do in this algorithm is we choose two stubs uniformly at random, and then we connect them to form an edge. And then we again choose two stubs from the remaining ones, and then we connect them. And so we keep doing this process of choosing two stubs uniformly at random and then connecting them to form an edge till all the stubs have been connected. Now, as you can see, this method can easily produce self-loops or multi-edges in the network. But that is not desired if the empirical network is a simple graph, because we want to compare apples with apples. So if the empirical network is a simple graph, we would want the graphs in the reference distribution to also be simple and not have loops and multi-edges. So what people do often is they would remove self-loops and they would collapse the multi-edges to simplify the network. But that clearly changes the degree distribution, right? The degrees are not same after that. And it also introduces other biases in the sampling process, which can often lead to incorrect conclusions about how well the degree sequence alone is able to explain the observed network statistic. So let's look at an example for that. So in the 15th century in Florence, among all the Florentine family, it was the Medici family that rose to high power in terms of commerce and banking. And so researchers have tried to explain how the Medicis rose to power. And there's this beautiful paper by Paget and Ansel that give the network explanation of how the Medicis became so powerful. So they say that the Medicis kind of occupied a very central position in the network of all the Florentine families. And this, by the way, is a network of 16 key Florentine families, and there is an edge between two families if there has been any marriage between the two families. And so this is a simple network. So since Paget and Ansel kind of give the network explanation of the Medicis being very central in the network, and that they kind of leverage this central position in terms of information flow, in terms of business deals, and like political relations, we're going to go ahead and ask the question whether the structural centrality of the Medicis can be explained by the degrees of the Florentine network alone. For that, we're going to calculate the harmonic centrality of each node in the network, and where like harmonic centrality gives us a sense of how close a node is to all the other nodes in the network. And so higher the harmonic centrality, closer the node is to all the other nodes of the network. And so we're going to go ahead and compute the difference between the observed harmonic centrality of each family and the mean harmonic centrality in the reference distribution, where this reference distribution is graphs with the same given degree sequence, but otherwise everything else is randomized. And first, we're going to like sample for this reference distribution using the stub matching algorithm that I talked about just a little while back. And here in the x-axis, we have the families. In the y-axis, we have the difference in harmonic centrality between the observed and that expected under the null. And here we see that for Medici family, the difference between the observed and that observed under null is pretty high. On the other hand, if we repeat the same experiment, but instead use our method to generate the reference distribution from the configuration model, and I'm going to talk about our method in a bit, we see that for all the nodes, the results have significantly changed. And especially for Medicis, we can see that the difference between the observed and that expected from the reference distribution is almost zero. And so from our experiment, we can conclude that the degree sequence is alone able to explain the structural centrality of the Medici family. But this example tells us that it's very important that we use the correct method for generating the reference distribution. Otherwise, we can land up in misleading conclusions. And if you're aware of the configuration model in the configuration model function in Python or in R, then they use the stub matching algorithm, which is again, not what we should be doing ideally. Okay, so one of the best approaches proposed so far for sampling graphs from the configuration model is this paper by Fosdick et al., where they propose a Markov chain Monte Carlo MCMC algorithm that can sample graphs from 8 different graph spaces. Among them, the firsts are the simple graphs, where no loops are allowed, no multi-edges are allowed. And even among the simple graphs, we can have 2 different kinds of graphs. One is the vertex labeled, where every vertex has a distinct label, and stub labeled, where every stub has a distinct label. Now, in a simple graph space, there is not much of a difference between a vertex labeled and a stub label. But when we look at the other graph space, for example, the multi-graphs, where loops are not allowed, but multi-edges are, in that case, it matters whether we are looking at vertex labeled graphs or stub labeled. In the stub labeled graphs, every stub has a distinct label. So in this example, stub P is connected to S and Q is connected to R. If we instead had P connected to R and Q connected to S, that would create a new network. That's a distinct network compared to this one we have here. But if we are looking at the vertex labeled only, it doesn't matter which stub is connected to which, as long as, for example, in this network, as long as there are two edges between 1 and node 2, it's the same graph. So just crossing over parallel edges doesn't create a distinct network in vertex label spaces. And similarly, we can have graphs where we allow loops, but we do not allow multi-edges. So there are loopy graphs. And then we can have both loops and multi-edges. So in total, we have 8 different graph spaces. And the MCMC proposed by Fosdick et al. kind of helps us to sample from all the 8 different graph spaces. Now, this MCMC that they have proposed has been designed in a way, or the transition probabilities of this MCMC has been designed in a way that the stationary distribution of this MCMC is going to be the uniform distribution over all graphs with a given degree sequence. So we have to let the MCMC run long enough that it converges on its stationary distribution, because then once it converges, it is going to sample correctly from the configuration model, because its stationary distribution is that target uniform distribution that we want over all graphs with a given degree sequence. I'm going to kind of assume a little bit here that the audience kind of knows how or what we mean by MCMC in its convergence. So coming back to this Fosdick et al. MCMC, a key factor of their MCMC is that there is this double edge swap in which we pick 2 edges uniformly at random from the network, and then we propose to swap them in either of the 2 possible ways as shown. Note that choosing 2 edges and just swapping them changes the connections or the the wiring of the network, but it still keeps the degree sequence the same. So this is how they propose a way of kind of randomly choosing new graphs with the same degree sequence by using the double edge swap method. And so this Markov chain kind of helps to explore all the graphs with a given degree sequence. So for illustration purpose, let us assume that we have this space of all graphs with a given degree sequence. And we start with the graph G0, and then we keep applying this double edge swap to generate more and more networks with the same degree sequence, right? So this Markov chain is kind of exploring the graph space with the given degree sequence. Until the point where the Markov chain has run long enough that it converges on that target distribution of uniform target distribution, which is the uniform distribution over all graphs with a given degree sequence. Another point I want to make here is that the graph space is not rectangular. In fact, the geometry of the graph space of all the graphs is kind of like, it's not known, but here just for the illustration purpose, I'm using a rectangular space. So the caveat of the MCMC proposed by Fosdick et al. Is that it will sample correctly from the configuration model only after the MCMC has converged. If we sample from this Markov chain before that MCMC has converged, then we are not going to generate correct samples from the configuration model. They're going to be biased in some ways, and that is not what we want. So we have to wait till the MCMC converged. And also that consecutive points in this Markov chain are very highly correlated, right? Because if you have one network and you apply a double edge swap, the next network is very similar to the first one. They just differ by one double edge swap, right? So the second network is not uniform random with respect to the first. They're instead very highly correlated. So we need to know how spaced the samples should be in this Markov chain before they are sufficiently independent of each other, and then we can consider them as uniform random samples. So right now, we don't know how long this MCMC should run before it converges and how spaced. That is the question we answer in this project. Our approach here is to first choose a network statistic to monitor the progression of MCMC over time. So we want to know how the network structure is changing as and when the swaps are applied. And for that, we need to choose a network statistic, to keep a track of that change in network structure. And then we estimate how far apart should samples be in this Markov chain before they become statistically independent. And we need to design a test to detect when this MCMC converges on the target stationary distribution. Okay, so let's come to our first question. Our goal here is to convert this the sequence of graphs sampled by the Markov chain to a scalar time series. Okay, so for each graph in the Markov chain, we are going to compute a network statistic so that we have a scalar time series from the Markov chain. And the network statistic that we choose is the degree assortativity, which is basically the tendency of nodes of similar degrees in the network to be connected to each other. So for example, if we have a star network, the degree assortativity would be -1, because the highest degree node is connected to all the lowest degree nodes. On the other hand, if we have a group of cliques where every node's degree is same as its neighbor, in that case, the degree assortativity would be +1. On the other hand, if we have a completely random network, it's more likely to have a degree assortativity close to 0 than to -1 or +1. So here's an example of how the degree assortativity of an empirical network of around 25,000 edges changes as and when more and more swaps are applied. We see that the value kind of quickly shifts from the original empirical value, and then it kind of stabilizes around a point. So this is the point where the MCMC has converged, in the sense that the distribution of the graphs it's sampling from is not changing anymore. And why do we choose degree assortativity? It's because it's very easy to calculate. So note that once we have a network and we know its degree assortativity, we apply a double-edged swap, we get a new graph. We need to calculate the network statistic of this new graph again. Now, if calculating this network statistic is computationally expensive, then that will make our method very slow, right? So we want to choose a network statistic that's very fast to calculate, and degree assortativity of this new graph can be calculated in constant time. So that is why we choose the degree assortativity to monitor the progression of MCMC. Okay, so now that we have chosen the network statistic, the next question we have is, how do we estimate how far apart the samples need to be in this Markov chain so that they're statistically independent? So for that, we would do an autocorrelation test where we would test for correlation at lag 1. For illustration purpose, let us imagine that we have a list of degree assortativity values such that the consecutive degree assortativity values are eta swaps apart. So say, for example, R1 is coming from a graph G, and R of 1 plus eta is the degree assortativity of a graph obtained after applying eta swaps on graph G. Okay, so consecutive degree assortativity in this list are the degree assortativities of graphs that are eta swaps apart in the Markov chain. Once we have this list, we are going to calculate the correlation coefficient of this list X as shown here, and the list Y, which is just a lagged version of list X, right? So if we find a high correlation between X and Y, then that means every point in this list is highly correlated with the next point. On the other hand, if correlation between X and Y is not statistically significant, we can say that eta swaps was enough to make the consecutive degree assortativities independent of each other. And yeah, so that gives us how spaced the sample should be so that things become independent. So our goal here is to try different values of eta and to find that smallest gap eta naught at which the lag 1 autocorrelation is not statistically significant. And we call that the sampling gap of the network. Okay, so we are going to go ahead and run this sampling gap experiment on a bunch of I think more than 500 networks across the 8 different graph spaces. And just a side note that the sampling gap experiment that we have designed is a little bit more complicated than this. And I'm just like avoiding the details here. I think we still get the idea of how we are designing the sampling gap algorithm. Okay, so now we're going to look at the results of applying this experiment of sampling gap on a corpus of different graphs across the 8 graph spaces. Okay, so here on the x-axis, we have the number of edges, and on the y, we have the sampling gap obtained from the sampling gap experiment, or the sampling gap algorithm that I just talked about. And here we see that for most networks, denoted by red dots here, there is a very strong linear pattern between the number of edges and the sampling gap obtained. It's so strong that we can almost propose an upper bound of twice m for 6 of the graph spaces, while an upper bound of 2.3 m for the remaining 2 graph spaces where we allow multi-edges and the networks are vertex labeled. The gray crosses that we see over here are graphs for which 2.3 m and 2 m are not going to be good upper bounds. And these are actually graphs that are very dense. And for these 2 spaces, these are graphs that have very high, like some of the nodes have very high degrees. And we were able to identify how exactly density or high density and high degree play a role in this sampling gap. But for the interest of time, I cannot go into the details of them, but I'll be happy to talk about them offline if anybody's interested. But the takeaway here is that for most networks, we are able to propose an upper bound from the strong linear pattern that we see here. And so for these networks, or for any new network at hand, we can directly obtain the sampling gap to be either twice m or 2.3 m, depending on the graph space, without having to even run the sampling gap algorithm from the scratch, right? So the strong linear pattern allows us to derive this decision tree for automatically obtaining the sampling gap eta naught for a network in hand. So again, I'm not going to go into the details of the decision tree, but basically we specify the graph space and we specify the graph whose degree sequence we want to keep fixed. And then depending on whether multi-edges are allowed or not, self-loops are allowed or not, and whether the network is stub labeled or vertex labeled, we can obtain the sampling gap directly in instantaneous time. Although for some networks where the graph is too dense and where the maximum degree or the degree is too high, in that cases, we will have to run the sampling gap algorithm from the scratch. But for most of the networks, we don't have to worry about that. Yeah, and how we come up with this threshold of high network density and high degree, I'm going to have to kind of omit that for the interest of time. But again, please feel free to reach out to me if you're interested to know. Okay, so this gives us an algorithm for estimating how far apart the samples need to be statistically independent in the Markov chain. The next question that we have is, how do we detect when this MCMC converges on a stationary distribution? So to do that, we are going to use the DFGLS test. It's called the Dickey-Fuller Generalized Least Square Test of Stationarity, which is used to detect stationarity in any time series. A time series is called stationary when the mean, the variance, and the covariance of the time series is not changing over time. So for illustration purpose, let us suppose that we have a time series of degree associativity as and when more and more swaps are applied. So we are going to look at a window of this time series, and we're going to apply the DFGLS test. If we are able to reject stationarity, we are going to slide the window further and then again do the test. And we're going to keep repeating this test of sliding the window and doing the test and rejecting based on where on the Markov chain process we are, until the point where stationarity cannot be rejected anymore. And that's where we say that our method has detected convergence. Now that we know how the method works, the question is, does it work well? So again, for illustration purpose, let us suppose that we have an empirical network of around 2,700 edges, and this is the empirical value of the degree associativity of this network, around 0.46, sorry. So this is the empirical observed degree associativity value. This is what the distribution of degree associativity looks like after m by 8 swaps have been applied on this empirical network. This is how this distribution looks like after m by 4, and then after m by 2 swaps are applied. So we see that the distribution is moving, and this progression of the distribution as and when more and more swaps are applied is indicative of the non-stationary nature of the Markov chain in this phase. And then after sufficient swaps have been applied, our method detects convergence. Note that applying further swaps to it does not change the distribution. So even after we have applied 1000 M swaps, the distribution didn't change. And so this is an indicative of the fact that our method correctly detected when the MCMC has converged on its stationary distribution. And so comparing the distribution at the point where convergence is detected by our method and at the point after 1000 M swaps have been applied can be done statistically using the chaos test, which is a test of distributions. It helps us know whether two distributions are actually kind of like overlapping or not. And so we are going to repeat this chaos test on all the graphs that we have in our corpus across all the 8 different graph spaces. If a chaos test is rejected, then that means that the distribution at the point where convergence is detected and after 1000 M swaps are different. So our method detected convergence way too early, even before the Markov chain entered its stationary distribution. On the other hand, if chaos test cannot be rejected, we say that our method accurately detected the convergence of the MCMC on its stationary distribution. And so this is the result of applying this chaos test on all different graph spaces, which we can see in the x-axis here, and all across all the graphs in the 8 graph spaces. And the y-axis is basically the fraction of graphs for which the chaos test was rejected, which is indicative of early convergence, or it kind of indicates that our method detected convergence way too early. And so we see here that across all the graph spaces, our method's rate of early convergence is well within the critical threshold, which is calculated using the type 1 error rate of the chaos test and the number of graphs we have in each graph space. And so this tells us that our method does accurately detect when the MCMC converges on its stationary distribution. So far we have looked at the degree assortativity only. But then what about the other network statistics? We want to ask the question that at the point where we detect convergence based on degree assortativity, have the other network statistics converged too? And so we look at 8 statistics in total, including the assortativity. We look at clustering coefficient, diameter, average path length, number of triangles, squares, and then edge connectivity and radius. And so these network statistics are very computationally expensive to calculate. So we are not going to keep calculating them throughout. Instead, we are going to use the degree assortativity to monitor the MCMC, but at the point where degree assortativity, or at the point where our method detects convergence based on degree assortativity, we are going to compute these network statistics and look at a distribution of the network statistics, and then again look at distribution after 1000 M swaps and do the same chaos test between these two distributions to know if our method detected convergence way too early or was it accurate. So again, the same kind of a plot like we saw before, except that now we're looking at all the different network statistics of interest, and we see that for all of them, our method detected convergence correctly, meaning that at the point where our method declared the convergence, all the network statistics had converged. Okay. Now, one common question people have, let me just have a look at the time. Okay. So at the point where, sorry, I take that back. A common question that's asked for any MCMC in general is how many steps does it take for the MCMC to converge? And in probability, it's kind of, it's called the mixing time of the Markov chain. And so here we're going to look at how many swaps did it take on average for the MCMC to converge, or at least for our method to detect convergence in the MCMC. And so here we have number of edges in the x-axis and the average number of swaps before convergence was detected in the y-axis. And the 20M line is kind of hand-fit line. It's not through any linear regression, but it's because we see a very strong linear pattern again, at least in the 6 graph spaces. In these 2 graph spaces, it is still linear, but of course 20M is kind of more like an upper bound than, more like a lower bound than an upper bound. And so we believe that these observations can be of helpful insights for network theorists or theoreticians who want to study the geometry of the graph space explored by the Markov chain, because that is still an open question. And the mixing time, there have been some papers that have tried to mathematically derive the mixing times of Markov chains that are kind of related to the configuration model, and they prove it to be polynomial in n. So it can be order of n squared, polynomial in n. But here we see it's more like, linear in terms of m, right? The number of edges. And so, yeah, that is why we believe that these experiments or the results can be of helpful insights to the people who are trying to kind of get an idea of what the geometry of the graph space is and what the mixing time of this Markov chain is. Okay, so that brings us to our third question, which is how do we detect the convergence of the MCMC? So to summarize, we propose a method for sampling graphs from the configuration model. We are basically using the degree assortativity to monitor the progression of the MCMC over time. And we are estimating how far apart the samples should be in this Markov chain. And we are calling that the sampling gap of the network. And we are using the DFGLS test to detect when the MCMC is converging on its stationary distribution, which is the target uniform distribution of all graphs with a given degree sequence. And then we show that our method accurately detects convergence across all 8 graph spaces. And then we also show that our method extends to other network statistics too, beyond just the degree assortativity. Yeah, so a version of our paper is up on arXiv, although it's not the latest version, and we are hoping to upload the latest version in a week or 2. I would like to thank my collaborators, and I would like to thank my funders, and I've had some very helpful conversations with Dan, Joel, Johan, Kevin, and Sam, so I really acknowledge them. Yeah, and I'm open to questions. Let me know if you have one. Thank you.
Thanks. This was a really cool talk, I must say, for me as a network. What did you say? Theoretist, or how did you call it?
Theoreticians or
theoreticians. Yes.
Yeah.
So my first question, if I just gonna steal this now, the first question was actually about a paper, but that you answered with your last slide. One question I have just for understanding, could you go back to, I think it was slide 39, where you were comparing different network statistics with their convergence time?
Convergence time.
Yeah, this one, yeah. I have an issue understanding how to read this graph and why degree, so could you just maybe explain a bit how to read this graph and why degree assortativity is just explain why when degree assortativity has detected convergence, the others did too, and what is the difference between the height? What does the y-axis mean?
Yeah, that's a very good question. So let's first look at one particular graph space, and then we are going to come at the others. If you're looking at a particular graph space, we have an upper bound, like there is a critical threshold. So if we have, say, 100 networks in a given graph space, there is only so many for which the KS test can be rejected. And that's you can derive that critical threshold using binomial distribution of the type 1 error rate of the KS test. But as long as it's below that threshold, it doesn't matter if it's 2% or 4% or 6%. As long as it's below the critical threshold, it means that at the point where convergence was detected based on degree assortativity, the other network statistics also look converged. So the distribution at the point of convergence and at the point where 1000 M swaps have been applied, these two distributions are same, which is indicative that the distribution became stationary. It didn't move after convergence was detected by our method. Yeah, so that is how I would interpret this plot. It doesn't matter where on the y-axis the value is, as long as it's below the threshold.
Okay, so is there then is there still a way? So I was thinking maybe that it shows which one is the fastest. Is there a way to say which statistic detects convergence the earliest? So say no one has detected except this one now. So is there a way?
Yeah, that's an interesting question. But I think the goal is to choose a network statistics that that's the slowest, right? Because we want to detect convergence when all the network statistics have converged, right? Because if the distribution of graphs has converged, then all network statistics distribution should have converged by that. We don't want to choose a network statistic that converges early, but at that point there can be other network statistics who have not yet converged. So that's kind of a wrong network statistic to choose. And this is actually an open question that you can go to the discussion section of our paper to read more about it. But we write that mathematically coming up with a network statistic that would be the best, in the sense that it's not too slow to compute, and yet it does not lead to wrongly detecting convergence, is kind of a great that would be great. But for now, we are just empirically seeing what do the other network statistics look like, and for 8 different statistics we found that all of them have converged. So yeah.
Okay, cool. That makes, of course, sense that it's the slowest. But can you say which one is then the slowest for me? I'm just curious,
Yeah, I don't know. I think
Okay.
the degree assortativity. I did run some experiments on how the network statistics are changing over time, and I saw that the diameter, the average path length, the radius, which is the distance-based network statistics, converge very fast. While the degree assortativity takes more time, clustering coefficient also I saw takes more time. But again, these are all anecdotal observations. I cannot give you mathematical proofs.
I did not expect that.
I saw that the distance-based ones kind of converge very early.
Okay.
Yeah.
Okay. Then there was one. That's now also more like an algorithmic one. I think you can also, of course, these other statistics are harder to compute, but it's in every step you only swap like 1 or 2 edges, right?
Yes, so just 2 edges.
Yeah. Then it should be easier also to update the others in a maybe not constant time, but rather fast. Or am I wrong? I
think clustering coefficient might be still easier. I don't think it's going to be order of 1 though, because you have to look at all the neighbors of the edges of the nodes incident on the edges that just got changed, because the triangles are going to get affected that way. For diameter, I think we need to calculate it from the scratch. I'm not sure.
I think that I also thought that my diameter.
I think for the diameter, it might.
It's not that important. I was just curious.
Yeah, of course. These are valid questions. Very, very valid.
Thanks. So now maybe someone else has any questions about this? Anyone in the room? No. Let me think. Martin, yeah?
Yeah, sorry. I got 2 questions actually. First of all is about applications, because actually, of course, I can see the use of this in terms of you thinking, oh yeah, across all possible uniform graphs. But when I think about a real situation, it may be that is not the graph space in which the data comes from.
Yes.
You could look at your marriage ties, and perhaps it isn't the class of all uniform graphs that the marriages are even possible from. So I just wonder if you'd thought about, what you think the main application of this is. I could see a mathematical application and a statistical application really easily, but I wondered about how it was in terms of actually statistically looking at particular configurations or properties of networks when those networks are derived from social processes.
Yeah, I think the example that I provided at first regarding the Medici is kind of one example where we are looking at a social network, and we are trying to answer whether the degree structure is alone able to explain the observed centralities of the family, and we were particularly interested at the Medici family. So I think our method, so this project is focused on developing that algorithm that would sample from the configuration model. Because right now, the only existing method is this Markov chain, and people are like, run it as long as you can, see what happens, and then kind of wait for a bit before you sample the next swap, the next network, because then it's going to be very correlated otherwise. And so this network, or our method, is kind of giving a practical solution for the MCMC that has been proposed by Fosdick et al. Now, this method can be used for in any place where a configuration model needs to be used for. Like I said, in the Medici example, like I'm not sure if you're wanting to, if you're looking for other social network examples, because that in that case,
it's just I think the space by which, say, for the Medici one is done, it's not a uniform distribution of possibilities in the first place. So if you looked at networks with no agency, so protein-protein interaction networks, then I could see it would be absolutely brilliant in terms of being able to, you know, there are two, I think mathematics is fascinating, and it's a really good piece of work. So congratulations, let me say that to start with. But I'm just trying to think beyond, you know, how we can use this to help our understanding of networks in real situations, as opposed to slightly abstract situations. But I can see where there's lots of abstract situations which it would work really well.
Yeah. I think one example I can think of is when we want to look at racial biases in a friendship network. So say, for example, we have a group of people or group of school-going students, and the network is a friendship network, and there is like an edge between two nodes denoting who is friends with whom. And we kind of want to know if we just keep the degrees of the nodes the same. So we specify the number of friends each student has, and otherwise we randomize the connections. Do we find a stronger assortativity in terms of race? A higher racial assortativity would be, you know, high, or racial assortativity would be high when people of the same race are being more friends with each other as compared to people of different race. And I think that can be an example of using the degrees, using the configuration model to answer, you know, whether such a strong racial bias would otherwise be seen if you just keep the degree same, but you otherwise just randomize. If you don't see the same racial assortativity, then you can say that the racial assortativity in the observed network is coming out from some bias that the students have in their head. It's not happening at random. The friendships are not happening at random, and there is some bias running before, you know, that's there.
Yeah, so I mean, it's rather treating it like you do a permutation test, because in a sense, you've got a network and you're looking with things internal, which I think is a really good idea and a good way of doing it. I have one very quick second question, which was, I can't see any problem with extending this to multi-mode networks, two-mode networks. Is there, I mean, obviously you may want to use different network statistics in that case, but have you thought about two-mode networks?
We have not. No, we have not. In fact, there are a lot of other MCMCs for some different, like instead of just keeping the degree sequence same, there are things that there are MCMCs that keep the core value of the node same, or it can be even extended to directed networks or hypergraphs. And there are MCMCs, I suppose, for those. For generating graphs from those configurations, but we haven't yet run the experiments, but we do feel that similar methods might be applicable to those cases too. So, you know, our methods might be extended to those multimode or hypergraphs, or, you know, weighted graphs even. So yeah, we have not explored that yet. Yeah.
Okay, do we have, okay, as we have one question on Zoom, Stepan?
Yes, hello. Thank you for a great talk, Upasana, and I have two questions. So the first question is, I wonder if your results also depend on the network size, because you showed that they depend on number of edges, but is convergence also sensitive to the network size. I imagine that the larger the network, the harder it is to to converge. And also the second question is about this average statistics, which are depicted here on the left plot. Do you compute them per network or per sampled network with a certain number of double H swaps? Because I'm seeing that here you use some samples, and then how many networks do you sample with a certain number of double H swaps here?
Yeah, that's a good question. So answering the second one first, we compute the network statistic for each network. So you apply one doublet swap, you calculate the new network statistic. You apply another doublet swap, you calculate the new statistic. So for each swap, we are calculating the network statistic, which is why it's important that we choose a network statistics that's computationally inexpensive. I hope that answers the second question. The first question, I forgot, sorry. Could you please repeat the first question?
It was about the size of the network, so number of nodes or vertices.
Yes, so if you look at this network, this plot, the average time to detect convergence is around 20 M for these 6 spaces. So first we need to detect convergence, and from there onwards we need to sample graphs at a space that is eta swaps apart, right? So it is going to be a function of M. So bigger the network, bigger the M, so bigger would be the time to sample from the this Markov chain. But it's relatively fast. Like I remember applying this to, it was a small graph. It had 5,000 edges, but in just some seconds, we were able to generate 1,000 samples from the configuration model. But again, it's going to grow linearly with M. But we still see that we still feel that it's pretty fast. It's not that you're going to have to wait for hours to generate 1,000 samples. So yeah.
Thanks for your questions, but I want still to clarify my second question. I was curious then why on this plot of convergence on degree assortativity statistics, why when you apply so many double H swaps, why it never reaches the initial empirical network if it has the same degree sequence?
Good question. That's a very good question. This is for one chain. This diagram over here is for one chain. If you keep running this a lot of times, you might sample the starting value, but it's going to, the fact that it almost never occurs is indicative of the fact that this degree assortativity in the observed network is very rare, given just the degree sequence. But again, yeah, this is just one example. If you run multiple chains, you would come across like some graphs that has the same degree sequence. Sorry, the same degree assortativity as the observed network.
Okay, thank you.
Okay, do we have any other questions? If not, then let me just